Good afternoon, everyone, and welcome to the SUT Plus October webinar on floating offshore wind energy. We're delighted to welcome Matt Barnott along this afternoon as our presenter. Matt is an experienced engineer at Flotation Energy with a wealth of knowledge and experience in the offshore renewables industry. Matt's presentation will be a developer's perspective on the cutting edge world of floating offshore wind energy. So before we start, I'll just go through a quick introduction to the SUT and SUT Plus. So the SUT is a multidisciplinary society bringing together organisations and professionals working in the underwater technology market. The SUT encompasses everything from ocean science and offshore site investigation to marine renewable energy and robotics and much, much more. So a very diverse professional organisation. Um, the SUT was founded in 1966, and we've got branches across the world. Our members include scientists, engineers, students, and many other professionals with an interest in underwater technology. Uh, so the SUT Plus is the young and developing professionals subset of the SUT Aberdeen branch. As I say, it's aimed at young professionals and students working in the subsea industry. This is our committee here at the moment. Um, so what's our aim? Well, our aim is to increase newcomers' interest and understanding of the underwater technology industry by putting on a range of different events throughout the year. All of these events have got a focus on knowledge sharing and professional development. We try and keep a fairly busy calendar of events to keep up engagement throughout the year. Um, Events that you might see during the year that we put on are technical presentations and debates, various site visits, our annual chartership workshop, various STEM events, and of course social and networking events. We're always looking for event suggestions, so if there's anything you'd like to see in the calendar, please do let us know going forward. And just before I hand you over to Matt, I'll just run through some upcoming SUT Aberdeen branch events. So first of all, on the 9th of October, we've got an evening meeting focused on carbon capture and storage. So this will include a few different presentations, such as offshore CO2 transport, well repurposing, and the role of digital technology in CCS developments. Looks like it's going to be a really interesting event, so definitely worth checking out. There's also evening meeting in November on the 13th, which is going to be focused on materials and welding. There'll be some more details about this coming out soon, so just keep up to date on the SUT social media and website going forward. Um, and on the topic of floating offshore wind, there's also an offshore wind renewables training course coming up, which I believe is going to be in May 2025 in Newcastle. So basically, just watch this space. There'll be more details about that coming up soon. Um, Here are social media details, so make sure and keep up to date with all of these. So before I hand you over to Matt, just to let you know this presentation will be recorded. So please mute your microphone and don't share any video. There will be a Q&A session at the end of the webinar, so feel free to post your questions using the Q&A function as we go, and then we'll aim to read them all out at the end, depending on time. So the plan is to run until about 2 or 2:15 sort of time. So I'll hand you over to Matt now for what's going to be a fascinating presentation. Thanks very much.
Brilliant. Thanks, Joseph. Let me share my screen. Hopefully you can all see that. So yeah, hi, I'm Matt Barnott. I'm an engineer working for Flotation Energy, and I'm here today to give a sort of high-level introduction to floating offshore wind. So I'm going to be covering a sort of range of topics. Initially, I'm going to just be talking a bit about Flotation Energy, just give a bit of context behind the company and where I fit into this. Then sort of a high-level offshore market general overview, and then going into a bit about floating offshore wind. So what are the benefits, what are some of the cost drivers, and sort of talking around the challenges as well. And then also going into the floating technology, so substructures, moorings, and anchors. And then also from a developer's perspective, what we look for in a substructure and how we make the decisions of which one we're going to use for which project. So without further ado, I'll start talking about flotation. So flotation was founded back in 2018 by Alan McCaskill and Nicol Stephen. So Alan, in a previous life before flotation, worked on the Beatrice demonstrator project, which was quite a groundbreaking project at the time. It was it was 5 megawatt turbines that were used to decarbonize the Beatrice oil and gas platform. So this was the first instance of targeted oil and gas decarbonisation. And at the time, it was the largest turbines. It was the first time using jackets, even deepest water. And during the sort of course of this project, Alan met Nicol, who was he was Deputy First Minister of Scotland at the time, and together they decided to embark on a mission to do floating offshore wind. So Kincardine was incepted and then completed in 2021. And off the back of this, they pretty much wanted to combine the two. So oil and gas decarbonisation using floating offshore wind. So you've probably seen Greenvolt in the news recently. Pretty much that is when that idea came together and Flotation Energy was formed. The idea was to basically bid for the Greenvolt site during the ScotWind leasing round. But again, as many of you may know, ScotWind was delayed, pushed back. So in the meantime, they applied with our joint venture partner Cobra for the Morecambe project in the UK round 4 leasing round, and we were successful. So that's 480 megawatts in the Irish Sea. And again, things were still delayed. So we ended up winning Whitecross, which was a 100 megawatt test and demonstrator in the Celtic Sea. And then when ScotWind rolled around, it wasn't really suitable for the sort of projects that Greenvolt intended to be. So we ended up not winning anything in ScotWind. However, throughout all of this, we were having conversations with the Scottish Government, and we helped sort of form the INTOG round. And as we know, we were successful in winning Greenvolt and a larger project, Senos, as well. So looking forward, we've got a large pipeline. We've got interests, around Europe, around the globe. In fact, we've got offices in Japan, Taiwan, Australia, and we're growing rapidly. So Flotation Energy, in fact, it'll be almost 2 years ago to the day, maybe in a couple of months' time, we were bought by TEPCO. So that's Tokyo Electric Power Company, which is the first largest sort of power company in Japan, and it's in the top 5 in the world. So it's a very big company. It's got a lot of expertise, mainly onshore wind and hydro, but basically they bought flotation for our expertise in floating offshore wind. So they are our parent company and they own us in full. Just to put a bit of context into things again, so these are our projects in the UK and Ireland. So you can see we've got Greenvolt and Senos up there in the North Sea. Those are our targeted oil and gas decarbonisation projects. Sorry, I'm also realising I've accidentally put a timer on these slides, so that's a bit frustrating. But so the idea behind Greenvolt and Senos is that we provide a grid connection to shore and empower to the oil and gas platforms. So when we're generating, we are powering the platforms and exporting to the grid. When we're not generating, we're able to import from the grid and basically decarbonize these platforms so they can start decommissioning the power gen, which is quite exciting. And then we spoke about Morecambe. So that's the 480 megawatt project. That's fixed based in the Irish Sea. Then we've got Whitecross, which is the 100 megawatt test and demonstrator, which is in the Celtic Sea. And also Greystones and Blackwater are Irish projects, which I've worked on. So a bit about me. I'm the vice chair of the SUT Plus committee, so I'm helping organise all the sort of events that Joseph mentioned there. But my day job is engineer at Flotation Energy. So throughout all this, I've worked across a number of projects. You can kind of see that on the timeline below. I've also hosted 40 trips out to Kincardine, which is the world's largest grid-connected floating offshore wind farm in the world. It's about 15 kilometres off the coast of Aberdeen. And I've even got a Kincardine tattoo. So there you go, commitment right there. So how did I get into this? I did my undergraduate in mechanical engineering with renewables at Dundee. That kind of gave me the sort of flavour for engineering and renewables, but I knew that I wanted to get into renewables. I wasn't sure where I was going to go, so I decided to do my MSc in Renewable Energy Engineering in Aberdeen. And then obviously COVID hit and it was quite tough to get a job. So after a lot of searching, I heard about Flotation Energy through a friend of mine who knew Alan, and they put me in contact. So eventually I joined the team in May 2021. My claim to fame there is that I was the 10th employee at the company, and we're now over 200. So it's just, in the last 3.5 years, it's just rapidly expanded. So yeah, so I started off on the fixed project, Morecambe. Then when we won Whitecross, I kind of started part-time and then ended up full-time. And through that time, I sort of looked at the early engineering work, so establishing the base of design, getting the owner's engineers in place, and also looking at the turbine selection and substructure selection packages. And then when Ireland started hot enough, I moved sort of part-time to Ireland to help them sort of do the same thing, establish the projects. And then that became my full time. And now more recently, I've started supporting the wider early opportunities team. So looking at opportunities around Europe predominantly. So getting into offshore wind in general. So there have been 75 gigawatts of offshore wind installed globally. You'll see that the majority of this is in China. So Europe used to be sort of leaders in this space, but then they were overtaken by China quite rapidly. And I think that's going to continue that trend. But I think more importantly, so looking at Europe, 34 gigawatts is in Europe. Around 80% of these are on monopiles, which you can see in the bottom figure there. It's effectively a long cylindrical tube that gets hammered into the ground. So it's fairly basic, fairly cheap, but it's only really suitable for 30 to 40 meters of water depth. If you're going to move into deeper waters, you require jackets typically, and so around 10% of installations are currently on jackets, around 6% are on gravity base. But the point that I really want to highlight here is that less than 0.4% currently of installed units are floating. There have only ever been 44 installed globally, which we hear a lot about floating offshore wind in the media, and it's obviously there's a big push after ScotWind. But the fact of the matter is that right now there isn't that much actually installed. There isn't that much experience. I think it's quite key to get that across, just so you understand where we are right now in the industry. And again, just to put that into context, the largest fixed offshore wind farm is about 1.3 gigawatts. That's Hornsea 2. I'm not counting the full Dogger Bank development because that's several different projects. But and this is going to be overtaken again by Hornsea 3, which is about 2.9 gigawatts. So that's growing rapidly. The largest floating offshore wind farm is 88 megawatts. That's Hywind Tampen, which is another targeted oil and gas decarbonisation project in Norway. So that's 8.8 megawatt turbines. So again, small scale compared to fixed, but it is growing and it is getting there. The issue is with fixed is that it's limited by water depth. So there's a limited potential, limited scope in most markets for actually installing fixed projects. But the majority of the world's offshore wind resource is in those deeper waters. So we do need floating if we're going to capture all that opportunity. So that's kind of the main point here. And just to highlight that opportunity, and I must caveat this slide. So this is taken from the World Bank data. They've done a lot of research into the technical potential of fixed and floating offshore wind. And although they cap fixed at 50 meters, and that's what this data represents, we know that's not accurate. Obviously, Seagreen's installed at almost 60 meters now, and there is scope to increase. But just to, I guess, get across visually what the opportunity looks like fixed versus floating in these key markets, you can see that floating really does represent the lion's share. And in the UK as well. So this is a really good map. I really like it because it shows the sort of waters up to 60 meters in blue and anything above that in pink in the UK exclusive economic zone. And you can see as well that the current offshore wind activity is highlighted by those little hatched areas. So you can see that the majority of the fixed locations or locations that are suitable for fixed are currently in use. And you've got to consider the fact that there are other users of the sea. There are shipping routes. There are, most importantly, fishermen or fisher folk. And, we can't use all the shallow areas because they are predominantly used by fishers. And so we do need to start creeping out into those deeper waters. And to do that economically, you do require floating. There are some other reasons. So I've touched on the fact, that it unlocks the access to these other areas. Also, wind resource is better out in these areas because there's less interaction with the landmass. So you have a much smoother, less disturbed flow of air, which can lead to higher capacity factor. And those who don't know what capacity factor is, that is the nameplate amount of energy that your wind farm can produce. It's the proportion of energy that you do produce compared to the amount of energy that you could possibly produce. So typically, in fixed, we're seeing between 30 and 40%. So they're only producing 34% of their potential, whereas in floating, because you can get further out into better wind resource, you can maybe see that creeping up towards 50 or 60. But this is still to be seen. I believe Hywind Scotland's got the highest capacity factor. I think that was around 58%, and that's a floating project. Also, again, this is very broadly speaking, but there's more efficient installation at site. You don't need all the big heavy lift vessels. So think about a big fixed jacket structure. You have to you have to take that out with a massive heavy lift vessel, install it. It takes a lot of time, install all the piles. It requires a lot more engagement with the heavy lift vessels, which have a much higher day rate than, for example, the tugs that you'd require to tow a floating substructure to site. So the idea is that it should hopefully cost less to actually physically install these things. Also, less environmental impact. So although we do have piled anchors, and I'll touch on those later on, drag abetment anchors or suction anchors, which have generally been used to date, don't require any piling or hammering, which is very harmful to aquatic life. And also decommissioning of those is a bit more simple. You can just lift up a drag abetment anchor, and I want to say I'm using simple terms. It's a lot more complicated than that, but it's a lot less harmful to the environment. And also, if you can use a floating system, you can install them further from shore, so you're no longer creating such an issue with visual impact, which is a massive point of contention. There's a point on here that's not covered, which is birds. You'll find that bird populations start to disperse further offshore. So again, you're less likely to have bird strikes. But also local content is obviously a key topic. The assembly of the substructure and the wind turbine, so the integration of these has to be done locally. And if we're looking at concrete substructures, then that can definitely be done locally. So there's a whole lot of potential for benefiting the local economies as well with floating that might not be as simple with fixed. So let's talk a bit about cost drivers then. So what is the cost difference between fixed and floating? It's a trick question. What's your water depth? A study by Exodus back in 2020, which I admit is probably a bit outdated, basically suggested that the current cutoff for price is around 90 meters. So if you install a floating wind farm at 90 meters and a fixed at 90 meters, then they will cost about the same. If you go into 100, then floating becomes more economically attractive. But what you'll also find is that obviously, there's a lot more complexity with floating, and we're not currently going into those sorts of water depths. But also, hopefully, as things become a bit more mature and we get a lot more experience, we'll be able to deliver far more efficiently. So why is it currently so expensive, and how do we bring those costs down? So currently floating offshore wind, as I sort of demonstrated earlier, has only been delivered at a small scale. And another thing to note is that the design is complex. So you can see, with a monopile, and I know that monopile designers might get a bit upset. It's a tube, it's a rolled steel plate, which is welded together. And that's a lot more basic and simple than a semi-submersible, which is obviously consisting of several buoyancy chambers, a ballasting system, and trusses, and there's a lot more welding involved. It's complex and it's expensive. And it also carries a lot of steel weight. So I'll go into weights a bit later on, but you're talking about 3,000 tons for a semi-submersible on the very, very light end for a 15 megawatt turbine. But you're looking at far lighter than that for a monopile, for example. I've also got cost of capital down there. So this is kind of touching on the economics a little bit. But lenders, when they offer you capital for your project, so these are multi-billion pound projects, they will obviously have a rate attached to that, and it's called the weighted average cost of capital. So when you get the money in from the lender, if it's a more risky project, then they'll have more strict terms on the interest rate. So you effectively pay more to borrow money if the opportunity is more risky, which currently floating is, because there have been less examples of successful deployment. So how do we bring these down? I like the term realization through demonstration and learning by doing. So we want to start small to then realize the benefits of making mistakes and lessons learned for the larger projects. So if you go out right now and try and do a 1 gigawatt floating project, you're going to make a lot of mistakes. There's not going to be too many learnings and efficiencies that have been realized already. So it's going to be very, very expensive. And for a project of that scale, you're multiplying your mistake per unit by 100, rather than, if you start off at small, like a demonstrator project, then you're only multiplying the mistake per unit by 10, for example. So you can really cut your teeth on the smaller projects to then benefit the larger projects. And in doing so, you're also building up a supply chain. So you're attracting investment, you're allowing for lessons learned, efficiencies, all these different things to be realized before you go big. But then when you do go big, you'll not only be able to take advantage of these efficiencies, but also the economies of scale. You'll get a supply chain going. You'll have the same people working on your projects and learning and getting better and better, and this will reduce costs. But then the big one I've got there is standardization. So there are currently hundreds of different designs that you can choose from for substructures. And so if every project goes for a different substructure type, where are the learnings? Where are the efficiencies? It's going to be slightly different each time. Whereas if we can standardize, as you see in jackets and monopiles, then it's going to be much easier to realize those efficiencies and economies of scale. So that's a little bit of an introduction. I'm just going to quickly run through infrastructure for anyone who's not familiar with your offshore wind farm sort of general components. So you've got the wind turbines, you've got substructures, you've got a mooring system, you've got anchors, inter-array cables, offshore substation, then you've got the sort of offshore cables that run to landfall, and then they get transitioned in a transition bay to onshore cables, which then you might have crossings, so you might need to drill and do all sorts, but then that routes through to your project's onshore substation, which then steps up from your transmission voltage up to the grid connection voltage. So all these different things form a floating offshore wind farm. For floating, I'm just going to specifically focus in on substructures, mooring lines and anchors, because these are, I suppose, the big ticket items for this, and where there's the most sort of variance in design from fixed. I know that obviously I've not mentioned inter-array cables there, but I will touch on those later on a little bit. So there are four basic archetypes of floating substructure. So we've got the spar up at the top, semi-submersible, barge, and tension-like platform. So spars, they're very stable, relatively mature technology as well. So you know that Hywind Scotland, Hywind Tampen, they both use spar. One was predominantly steel, one was predominantly concrete, but they're fairly well understood. And obviously spars have been used in oil and gas for a long time as well. The issue with these, though, is that they might not be suitable for a UK project or a project that doesn't have the fjords that Norway have. So you require quite a deep, water depth to actually integrate the turbine with them and actually manufacture them in general. So these aren't suitable necessarily for every project. One that is more applicable and one that you'll recognize, almost anywhere is the semi-submersible, which has definitely been used in oil and gas as well, extensively. But these are relatively light, they're port friendly. You can adjust the width and various parameters to reduce the draft. However, they're currently fairly complex and serial production can be challenging. And they're not as stable as spar either. But again, this is all, you can change all these parameters through design, and I'll go into that a little bit later as well. Barge, so again, shallow draft is tested technology. So that one there that you can see was deployed in Japan. However, these tend to be fairly large and they get battered about by the waves. So they've got a big block coefficient and water plane area. So they do get battered about. And yeah, I'll just move on to tension-like platforms. So we've just seen PGL in France deploy some tension-like platforms. I think these are potentially going to be a big game changer for floating offshore wind because they're very lightweight design, very stable in operation, and have a small footprint on the seabed, which fishermen like, which is good. However, they are less developed. There are challenges with installation, and right now we're sort of figuring out what the tendons should look like on a tension-like platform. Are we going to use steel wire? Are we going to use different polymers? How are we going to do it? And also, if you think about it, when you're installing a tension-like platform, you've got so much tension on each of the members, you need to install several at the same time. You can't kind of do them individually. So there's a lot more coordination there in the installation. And again, typically what we do is we would integrate the turbine with the substructure in port. And if you've got a really light platform, as you do with a TLP, it's got a much larger overturning moment. And there's sort of less resistance from the bottom, so it's less stable during tow, pretty much. So there are challenges there, but I think that once we can crack that, it's going to be a real game changer. So how do we design a substructure? Obviously, predominantly it's the site conditions. So the substructures are designed in line with certain DLCs, so design load calculations. which take into account the 50-year storm on site and combined wind and wave loading. So your meta-ocean regime will basically define the size of your substructure and what it needs to withstand, along with the turbine operational limits. So turbines, they're not allowed to accelerate too quickly as they move across, and they're not allowed to obviously tilt too much or move around too much. So all this needs to be considered in line with the 50-year storm. There's also a question of where you place your turbine. I've got a little model here, which I probably should have been using for all those demonstrations there, but you can see that typically you'd place it on a corner. But what we found is that when turbines get bigger and heavier, when you're integrating them, so when you're actually sticking the components onto it, the ballasting operation to keep it level as you're adding all these components actually becomes more challenging. Whereas if you stick your turbine in the middle, it's easier to level out in between adding components. So yeah, so we're seeing a move from corner placement to centroidal placement, which is quite interesting. You've also got questions about material, concrete versus steel. This is a really hot topic again. So steel, obviously shipyards prefer to use it. It's a lot denser than concrete, so you use less of it for the same kind of mechanical or material properties. So it turns out that actually, although it's heavier than concrete, your substructures will be lighter than using a concrete substructure. So concrete substructures can be anywhere up to 15,000 tons for a 15 megawatt turbine, whereas again steel can be around 300,000 tons. Yeah, sorry, no, 3,000 tons. Also modularity. So a big lesson learned from Kincardine is that we don't want to be doing what you can see here in this diagram on the right, which is manufacturing these all as one big, huge component and then towing these around to a site. We want to be able to manufacture the buoyancy chambers and the trusses and the block components individually, and then ship these to a nearby site for assembly. And then how do you increase the assembly rate? Use connectors, and you can use bolted connections, grouted connections. All this is still being figured out, but the idea is to accelerate the assembly time of this, and ideally the assembly time would be faster than the integration rate as well. So you've got a bit of a stockpile, but I'll go into that a little bit later on as well. So how do we increase the rate of integration? Well, I've kind of touched on it there. When you move a turbine to be more centroidal, it will increase it because you've got less ballasting operations to contend with. But also you can potentially design your substructure to be grounded out at the quayside, which would reduce the dynamics almost entirely. Or yeah, I mean, there are other smart ways of doing it, but this has to be a real focus because the delivery timeline of your project will be almost entirely linked to your turbine integration rate, because that is the longest lead item. So on Kincardine, for example, it took about 3 weeks for each turbine to be integrated. We need this to be reduced to maybe 7 days. So there's a lot of work to be done there. And again, we need to design the substructure around the port. We can't be spending millions and millions every time, the substructure of the turbine gets bigger. We need to be trying to design these things around what we've got already to try and, I guess, bridge the gap between where we are now to where we need to be. Because we can upgrade ports, but it takes time, and changes are the demands are constantly changing. So we need to make use of what we've got. So onto mooring system. So let's say that you've selected your substructure. Now it's time to look into the mooring system. You've got a few options. So catenary, it's fairly simple. So catenary mooring system is effectively a big heavy length of chain which sort of sags in that bend, and that bend is called the catenary. But yeah, typically these are only suitable for shallower sites because obviously lengths of heavy chain at the size that we're looking at are expensive, heavy, hard to come by. There are a limited number of vessels that can install these. So if you can move to semi-taut, then that will reduce your costs. So that's kind of the next one, which is kind of like a hybrid between taut and and catenary. So semi-taut has a length of chain and a length of synthetic fiber rope or wire or whatever you want to call it, but it just reduces the amount of chain that you need, and also reduces the footprint somewhat as well, which again fishers like. But it is less field proven. A major driver of your mooring system design will be the peak loads that you experience. So again, that's to do with the meta-ocean regime and the motions of your substructure. So semi-taut will have higher peak loads because there's less damping in the system. So you might need to start looking at load reduction devices or likes, and that's particularly the case with taut, which have just some synthetic fiber or wire in them. But again, lightweight, they're potentially a bit cheaper. But then you move away into different anchor types, which I'll touch on again in a little bit. So as I was saying, the site conditions and the ground conditions mainly drive your mooring design. So you've also got excursion limits to contend with. So you'll see in this bottom picture here, this is what we call a lazy S, which is this is the inter-array cable. And so obviously each one of these floating substructures has to have a J tube, which the power cable is sort of exits the platform. So it takes the power from the turbine and it kind of connects it to the offshore substation. Obviously, the platform is moving around a little bit. It's floating. It's not fixed. So these need to be able to kind of bend and extend and so as not to get damaged. And your mooring design will be heavily driven by how much you're allowed to move your cable. Because obviously, if you hyperextend it, you'll break it. And that's a very expensive mistake to make. So yeah, the excursion limit is extremely important. You also need to decide how many mooring lines you want. You might be able to reduce your chain size if you go for more, but then you've obviously got more chain in total. You've got more hours installing it. All these different considerations. And I touched on load reduction devices. You can see this is the TFI C-spring design, and this is the Dublin Offshore kind of damping design. So these basically reduce those peak loads, which means that you can move from maybe catenary to semi-taut or taut, but it also means that you can reduce your substructure size as well. So all these things need to be considered, but also ease of connection and disconnection. So it's a bit of a controversial topic, I'd say, but your general model for operation maintenance right now is considered to be tow back to port. So once you've got it installed and you've been operating, if you then have a major component that you need to be replaced, you would typically now have to tow it all the way back to the port, do that operation, and then tow it back and connect it up. So if that's the model that you want to go for, which isn't necessarily preferable, it's extremely expensive, then you need to make sure that you factor that into your mooring design. So make sure that you can quickly release and reconnect just to ease that operation. So you've got your substructure, you've got your mooring lines, and now looking at anchors. So again, drag abetment anchor. It's simple to install. You obviously lower it using an anchor handling vessel, and then you pull it up to the test load until it's embedded. However, these don't have any lateral loading. So pretty much they're very good at being pulled in this direction. They'll be stuck in the seabed, but as soon as you apply any vertical loading, they come undone, and it's not very good. So that's why the catenary mooring lines have to be so long. A lot of the chain length is actually on the seabed. And ideally, you would never, ever activate your anchors. It is just purely the weight of those chains holding everything in place. But if you do have, let's say you get hit by, the 10,000-year storm, which I know is pretty crazy, but with global warming, you never know. You might get to a point where you get lifted up, and then you might lose moorings. And yeah, it wouldn't be a good thing. But this also limits you to sort of your catenary mooring line system. So you wouldn't really want to use this for taut or semi-taut. It just wouldn't work. So that's when you need to move into suction anchors. So it's less invasive than piling, which is good, because piling you have to hammer things in, and that's not very good for the marine life. Whereas the suction anchor is pretty much just a bucket which you flip upside down, suck all the water out, and it latches down on the seabed like a limpet, which is quite cool. And it can be removed during decommissioning, so you can depressurize and basically pull it up, or you can cut it. It just depends on what you agree with the environmental statutory bodies. But they do require very specific seabed conditions, so they're not appropriate for everywhere. They can be used in sand or clays, but not rock or sort of gravelly stuff, because they need that suction. So it's a good option, but not necessarily the best option. The driven pile anchor, again, so we really want to avoid piling where possible, just because of the impacts to marine life. But if you have to, then pile anchors are pretty good. They're fairly cheap, actually, but they do require the use of a heavy lift vessel. But they are applicable to the wide range of seabed conditions. You could even pile through some soft bedrock. So and if you can't drive it, then you can also drill it. So they're quite versatile, but it is noisy and it is harmful, and it should be avoided if possible. Gravity anchors, now these haven't really been used too much, but they are considered. but yeah, no piling, but they're high cost and susceptible to scour. So scour, for those who don't know, is when the sort of currents go around your structure and it digs out all the material around it. So if you've got a gravity anchor, it might sink, which would then obviously change the dynamics of your system. So we need to try and guard against that. And so you can do rock dumping and scour protection and things. But yeah, it does add a bit of complexity and increases your requirement for inspection during operation. And again, so just going through some of these design considerations, Met-ocean regime, so it kind of all flows through. The motions on your floater will impact the way that you need to have your mooring line designed and the type of anchor that you'll be able to use. And obviously the ground conditions, you've got a few different options around here. You can kind of see how this will be used, but then also need to think about weight. So what sort of vessels are you going to have to use to install them? If they're extremely heavy, then that limits the number that are available, also increases cost and could lead to delays because you might not have the availability that you need when you need it. Also the cost of your anchors. So if you think about it, you've got, let's take Greenvolt, for example, 560 megawatts. You've maybe got 35 turbines, 35 substructures, and if each one has 3 mooring lines, and that's over 100 anchors. So your cost per anchor does have a significant impact on your capex. So that needs to be considered. Also complexity, you need to be manufacturing 100 of these things. You want to make them simple as possible. So that also obviously needs to be a consideration because that will impact program and cost. Loading. What about shared moorings? We know that Hywind Tampen are using shared suction anchor moorings, or at least they were planning to. I think they executed that plan, but you can create some efficiencies there. But then you also need to consider that in your design, and that might increase the size or the complexity of the design. So all these things kind of filter into each other. Environmental impact, you might be in an area that's been identified as being sensitive, in which case you might not be allowed to do piling, in which case that could actually drive your anchor selection. But then you might be told, well, actually your seabed's not good enough for suction, so you have to go for drilled, and then that can add complexity and cost. So all these things need to be considered. So considering all these things, so we've sort of gone through the different types, the options, how they're designed. Now, how as a developer do we actually go ahead and select what we're going to use for our project? So I've not written it down here, but the basic process that we follow is we start off with a long list. So we identify all the potential substructure designs that are available. And then we put them through a screening process, mainly based on TRL, which I'll touch on in a second. And then we produce a short list. We then invite the substructure designers to interviews, to submit documentation, which we review and assess against a matrix, which looks into all these different considerations and more. To then produce a short list. We then get them to do a competitive design process based on the site conditions and a turbine model. And then basically based on the output of those designs, we then select a single substructure to then be taken through to more detailed design phases. So that's kind of the overall process. But looking at these individual considerations, so technology readiness level, TRL, it's a scale from 1 to 9. You can see it there on your screens. And it was developed by NASA in the 70s. What it does really is standardize how we look at the development of a design. So it starts off, as a concept, and then it works through the basic design, and then they start getting into prototyping. And once you've done a prototype, you're then kind of ready for the full system, like at full scale. And at that point, we start to get interested because we believe that that's de-risked enough now for us to start considering for our project. So typically, we wouldn't consider a substructure that hasn't reached a TRL of 6, as in they haven't had almost a full size demonstrator in the water. But we're aware that TRL isn't everything. TRL, as you can see, is quite a rigid scale. But if you take Principal Power, for instance, they've obviously got the Windfloat Atlantic projects. This is their substructure pretty much. It's been done before, but they've recently changed to have a centroidal turbine for the reasons that I mentioned previously. So we know that that design has got all the benefit of the learnings from previous designs, but it's technically got a TRL that's extremely low. So we need to be a bit pragmatic when applying this to our assessment. So again, looking at dimensions, let's say that we've got the sort of designs back in this competitive design process, and we see that some are 90 meters, some are 120 meters. We might then be limited on what ports we can use. We might be limited on what plant we can use to move these things around. There are spatial limitations. All these things kind of feed into our assessment. And again, weight. So steel, much lighter than concrete, as you can see, and shipyards prefer working with it. So this might be a benefit for us to use because it's simpler. It increases our options. Because if we go for something that reduces our options, then that limits us and it leads to higher risk of cost increasing or program being lost. So we need to keep an eye on that. And also we assess these things for sustainability, carbon footprint. So the carbon footprint of steel is obviously a bit higher than the carbon footprint of concrete, but when you look at a concrete substructure, there's actually almost the same amount of steel weight as in just a steel substructure, just in rebar. Although we're aware that rebar is lower grade steel, but either way, all these things need to be considered, and also recycling. It's easier to recycle a steel substructure. But these weight and dimensions also impact draft and the available plant required to actually move these things around and load and offload. So particularly in offloading your substructure from the quayside, if you have a big heavy concrete substructure and you need to use the self-propelled motorized trailers to get it onto a barge, the heavier it is, the more dangerous that operation is, and the more limited you are in the barges that you can use. So the weight really does have an impact. And again, ports, I strongly believe are the key to unlocking floating offshore wind. Like without ports, you've got nothing. You cannot do any of these operations, the assembly, the integration, and the storing of all these huge components without a port. They're just too big to do inland and then transport to a port afterwards. So ports are absolutely key. And again, I'm going to say it again, substructure should be designed around the port and not the other way around. If you start designing the ports around the substructures, things get expensive, things get delayed, and then you enter into this chicken and egg situation that we're all, I'm sure, aware of, where the ports won't invest until they've got a set pipeline of projects. Projects won't invest in the port until they know they've got what they need. So let's try and mitigate this by just making the use of what we've got now. Quite an interesting standard, and I recommend anyone who's struggling to sleep reads through this. DNV-STN N001. It's the driving standard for draft and access. So like all towed operations, we have to basically align with this. And I mean, although again, there's a bit of pragmatism in there, we can speak with a marine warranty surveyor. These are kind of like the binding requirements for our operations within ports and obviously in the tow to site as well. So this mandates that outside of your integration area, you need an underkeel clearance of 1 meter up to 3 meters, with the minimum being 10% of your draft. So that means basically we have to have a draft in port of around 10 meters minimum. Again, we can increase the width of our substructures and change them around slightly to reduce the draft, but this can be a limiting factor, and we use this to screen out potential ports for these operations. And again, side clearance is 3 times the beam. So the beam, for those not aware, is basically the maximum width of your substructure. So you need an access channel of 3 times that beam on paper, although there's some pragmatism around that. So again, that limits the number of ports that you can use. There needs to be wide enough access, there needs to be enough water depth, and many more as well. So you need to have enough storage. Each one of these substructures, when fully assembled, will take up about 1 hectare of land before you load it off. And you need about 2 hectares of land to do the actual assembly operation itself. So it's extremely space consuming, shall we say. You need to have a huge port with sufficient load bearing capacity as well. So you need about 10 tons per square meter in your sort of storage and assembly area, and maybe 20, 15 to 25 tons per square meter in your load off quay, just because you've got more concentrated weights there. But again, the aim is to avoid having to reinforce. So if you have to use a ring crane for integration, for example, then you're going to have to put in a pile potentially to reinforce the quay. And again, that's expensive, it's time consuming. And if there's another way of doing it, then we should probably go for that. So manufacturing, it needs to accelerate. I think everyone's aware of this. It currently takes months. So each of those Kincardine turbines took about 3 months to assemble and manufacture. But again, that was all done in one block. But we need to reduce this to weeks. So if we want to install 500 megawatts per year, which is our current plan, then we need to be doing 1 a week. So we need to make sure that we can assemble these rapidly, integrate them rapidly, and get them out to site. And for this, I've kind of touched on it earlier, but modular substructures are preferred. So this is where we manufacture the sub-assemblies and then get these to the assembly yard, which is close to site. This way, we don't need to worry about towing these massive structures huge distances, because you're really limited on speed when you're doing that. And you can also damage the substructure in that process. So close to site, small components, and then, yeah, get them out rapidly. That's the idea. And again, we're looking to minimize welding and use connectors where possible. And again, concrete versus steel. Concrete substructures, there's great scope because concrete's fairly widely available, and although it is, it depends on where you're sitting, but it is expensive to set up some sort of slip forming manufacturing plant for concrete. But you can do that locally, and then you can actually produce them as blocks, full substructures fairly locally, whereas you can't do that really with steel in the UK, certainly. And again, are we looking at flat plate or rolled steel? This will impact the sort of the diameter, shall we say, of the buoyancy chambers. If you use flat plates, it's easier to do larger buoyancy chambers, whereas with rolled steel, it's more challenging just because of the size of machinery required. So if you do need to go for larger ones to manufacture, then maybe it's better to change to flat plates. But then that again can maybe limit the number of options that you've got. But yeah, I suppose a key point here as well is the assembly rate should be faster than the integration rate. We're wanting substructures to be kind of sitting ready to go, ready to be integrated, because again, like the integration is the longest lead item on our sort of installation critical path. So if we can have them in stockpile, and again, that doesn't necessarily mean wet storage, that can be dry storage as well. We're looking at options for both. But as long as they're there ready, then we should hopefully be able to do an efficient integration process. But yeah, efficiency of the flow is important. We need logistics to be nailed down, because otherwise mistakes start to accrue. And if you miss weather windows because of issues that could have been, mitigated by having a more efficient process in place or a more thought out process, then you end up having to obviously either start trying to install in the shoulder months, so anytime after September, October, or you then lose that entire winter period, and then you lose a year pretty much on program as you have to continue in the following year. So making sure it's efficient is key. So the performance, maintenance, and health and safety. Now, I would have put health and safety at the top because it is obviously like the top priority, but this is just kind of the list that I put together in no particular order. So substructure, it needs to meet certain operational limits. So these are stipulated by the turbine manufacturers. The nacelle can't accelerate too quickly. So obviously, if it's swaying around too much, then it sloshes oil about. And what we found actually in Kincardine is that it moved around to a point where oil was triggering sensors in the substructure, in the turbine nacelle, and it was shutting off, requiring a manual override. So moving too much isn't good. But that also lends itself to the fact that floating turbines need to be equipped to deal with that. So there's work to be done on substructures and turbines. And then declination, that's the angle that you can have. And it's the same issue. You can't have too much of an angle in your turbine. And then excursion as well, so how much it moves around. But these need to, again, the substructure and the mooring system need to be able to account for minimizing excursion in line with the inter-array cable operational limits. And also the key is to minimize downtime. So again, studies indicate that ballasting systems are a major point of failure. They're fairly complex, they can get clogged, they can shut down, and they require manual intervention. So they require actually sending someone out to go and fix them or unclog them, which again is expensive. And the higher your downtime, the higher your levelized cost of energy is. So again, reducing that downtime is key. And I think as well, we need to be looking at remote monitoring and digital twinning. So are these systems set up to account for those? Where can we put them? How do they work? How do we link this up with the O&M team? Like, these are all questions that we ask. Like, what are your plans for monitoring your system? And have you got plans in place for digital twinning? Because we know this is the future. Substructures obviously designed with safety in mind. So every time we get serious with a substructure designer, we have a full system hazards identification workshop where we walk through everything from the initial fabrication of the components to the assembly to the integration, all these different things. And we need to consider, how are workers actually welding these components? How are they fixing these bolted connections in place? Do they have to be underneath a suspended weight? Do they have to be in a confined space? We need to reduce all these things. And of course, again, a hot topic for health and safety with offshore wind is access and egress. Typically you'd have a CTV, so a crew transfer vessel, bumping up alongside your substructure, and then while they're both kind of moving, you then have someone running up the side of a ladder, which is obviously dangerous. So we also need to see, well, what are the compatibilities with SOVs that have walk-to-work systems? Are there hoisting systems that are compatible with your system? These are all the sort of questions that we ask to try and make sure that the safety of all workers involved is prioritized. And again, this kind of leads on to ease of maintenance. We want this to be easily maintained. We want as few moving parts as possible, all to maximize that uptime, because that has a huge impact on your levelized cost of energy. And again, major component replacement. So I put this one at the end here because it is a really interesting topic. So currently, as I mentioned previously, we need to tow these systems all the way back to port in order to actually do a major component replacement. And we've seen this on Kincardine a number of times, and it is just extremely expensive. It affects the fatigue life of your tower. It affects a whole number of things across your system. So how do we do this in place, in situ, is really the question. And Kincardine has now done the world first floating offshore wind major component replacement in situ. You can see it here. There's a little snapshot of using an up tower crane. So basically, all your turbines on the nacelle have a little davit crane that's capable of lifting maybe 10 tons or so. It could be more. These aren't exact figures, but the idea is that you use this crane to pick up components of a much larger crane, which you then build on top of your nacelle, which can then be used to lift out the generator, gearbox, whatever it is you need to replace, and then lift in a new one, and then dismantles itself again the same way. So we're trying to find smart ways of avoiding towing these things back to port, because it's not ideal. And also on Kincardine, maybe a bit of an aside, but the inter-array cables themselves don't have connector technology that allows you to plug and play, as the sort of buzzwords go. So you can't just unplug them, tow it back to port, come back, plug it back in. Every time a Kincardine turbine needs to go back to port for a major component replacement, they have to cut the cable, shimmy all the jewellery along, so that lazy S, because the buoyancy is important in this system. And then basically when it comes back in, they have to cut it again to get rid of all the waterlogged bits, and then re-splice it into the junction box. So you're actually shortening the length of your cable each time, which is just not sustainable. If you need to, replace several components over the lifetime of the project, it's going to be reducing the excursion limit which you've designed for. So it's not sustainable. So there's a number of upgrades that have been identified through Kincardine. So one of the last points I wanted to touch on was local content. So why focus on it? Well, the communities most affected by your project need to see some benefit of your project. And so by ensuring that a lot of the activities happen around that community means that you can provide jobs, you can provide employment, not just direct employment of engineers and fabricators, but also indirect employment. So if you bring more business to their town, then you'll find that cafes start to get more business, hotels, all these sort of ancillary industries do benefit from having more activity in that area. You're also less likely to encounter objection. I'm a huge proponent for community energy projects. So if we can bring the community on board, then we're more likely to engage encouragement rather than objection. And your consent's more likely to go through. You've got buy-in. You're actually benefiting the communities affected, which is really good. But also the creation of a local knowledge base. So Aberdeen, I think, is a really good example of this. I think 80% of the Scotland projects are within 200 nautical miles of Aberdeen. So there's a real opportunity here for us to get a knowledge base, which will again enhance and drive forward and accelerate these lessons learned that will then be applied to larger projects going forward. And also from a selfish developer perspective, non-price factors heavily weigh. Apologies. Weigh heavily on local content. Sorry, 2 seconds. Right. And yeah, also so selecting the right location for the right activities. So if you can get an area to focus in on moorings, for example, then they're going to get really good at moorings. If you can get them to focus in on assembly, then they're going to get really good at that. And yeah, basically, I think you want to select one site to get really good at one component of delivery. And that'll benefit the economy and also your project. So it's kind of a mutually beneficial piece. But the O&M base will always be local. It has to be, especially as you get further offshore. making sure that you're as close to the project as possible with that is important. And again, I touched on concrete substructures being more, it's easier to manufacture those locally because you can put a batching plant and your slip forming plant more locally. And I suppose as long as you've got the space, it's easier to do that than to bring in a big, massive steel manufacturing plant. But yeah, it's always key to ensure that designs have the local infrastructure in mind. So you're not planning on delivering the whole thing out of Asia. It needs to be done locally. It has to be done locally. And then finally, just delivery strategy. So once you've identified these facilities, you need to make sure that your that your integration methodologies and durations are nailed down. Because like I said, that's the key driver. You need to identify which vessels are required. The phasing of delivery and installation, making sure that you don't have a backlog of things that are waiting to get into the site, making sure that you don't have vessels on high day rates waiting around. You need to be smart about it, especially as the projects get bigger. But also, making sure that you're hitting those weather windows, because if you miss a weather window, then you're losing a lot on program, and that piles up, especially for larger projects. But yeah, 500 megawatts per year, that's one a week. That's the big challenge, and that's the goal. But yeah, in terms of what this means for actually selecting a substructure, we ask that all of these substructure designers consider these factors and provide us with their with information on these so we can properly assess them and make sure that they fit into our plans and our understanding. And it's more of a test as well. So if you're asking these questions, it requires the substructure designers to really think about how their design can be delivered. And we find that those with the best plans tend to be the ones that we progress because we know that they've designed it with deliverability in mind. And again, contracting strategy. So it's potentially more attractive if they can do the engineering, procurement, construction, and installation, but it's not necessary. A lot of them are purely designers who basically license their design to their manufacturer. But if we can reduce the number of interfaces, then that generally reduces the risk, although it can increase the cost. So that is also a big consideration for how we approach these things. So in summary, the offshore wind market is growing rapidly. Floating has a massive potential, but it's not without its challenges. We're still figuring it all out. But we need to focus on cost reduction first and foremost, I think, but also initially deliverability. If we're not able to deliver these first projects because we're too focused on cost reduction, then we're not going to be able to deliver larger projects because we just won't have the experience required. There are many configurations to consider. I think that we potentially need to start standardizing these. But for now, it'll be interesting to see what comes out on top anyway in the end. But again, finally, it is complex. So selecting the right system for the right project is challenging, as you've probably been able to see by that, the summary of things that we look at and all the different considerations. But I believe that's all I've got. So thanks for listening, and yeah, happy for any questions.
Thank you very much, Matt. That was fascinating. Really in-depth, interesting presentation there. I think everybody definitely learned something. It's clear from the number of questions that we've got.